Okay, so hopefully you've had a go at deriving the masses of Sirius A and B from the information given. So we need to be thinking about using Kepler's third law down here. So we're going to need the physical separation of the two stars. Okay, but I only gave you the angular separations of the semi-major axes of both orbits. So if we want the angular separation of the two stars, you need to add those up. Okay, so this is the same thing as A equals R1 plus R2, if you like, okay, that we looked earlier, but this is in the angular form first, okay, because that's what we're given. So the angular separation between the two stars when everything's deprojected is 7.5 arcseconds. So go back to our hopefully familiar formula now to change an angular separation into a physical separation. So that's just going to be theta times d when theta is in radians. Okay, so 7.5 arcseconds divided by the conversion factor, arcseconds in a radian, and multiply by the distance. So I told you it was 2.6 parsecs away. Put everything in SI units to come out in meters. Okay. So the physical separation here is 3 times 10 to the 12. In fact, we had that before, I think, on a previous example. So then we can put all that information in here. So we've got the separation of the two binary stars. We know the period is 50 years. So just put A in meters in here and convert the 50 years into seconds. And out comes a number. 6 times 10 to the 30 kilograms. Remember, there's 2 10 to the 30 kilograms in the sun. So that's 3.0 solar masses. Is the sum of the two masses. Okay. And now we need to work out the individual masses. And so for that, we're going to use the mass ratio. Okay. So mass ratio is given by the ratio of the orbital radii, which again, because they're both at the same distance, is the same as the angular ratio of their angular orbital radii, which is just 2.505, which is 0.5. So one star is half the mass of the other one, okay, which is what that says. So then you can substitute that in to M1 plus M2, so you can replace M2 with this. So you end up with 1.5 M1 is 3 solar masses. That means M1 is 2 solar masses, and M2 is 1 solar mass. Okay? So you can come out and solve for both masses individually. Okay. So this is telling us that Sirius A, which is star 1 here, is a 2 solar mass star. Okay. And remember, Sirius A is the very bright, sort of bluish sort of object, sort of a white star anyway. And so that's that's actually a 2 solar mass main sequence A-type star. But the other star is 1 solar mass, okay, but it's much fainter. Okay. So that's telling us already that it can't be a main sequence star, okay, because it's much fainter. You saw a picture in an earlier lecture, and that is telling us that it must be much smaller. So this is actually a white dwarf star. So Sirius B is a 1 solar mass white dwarf star. Okay. And again, you can work back through here that this star must have started out as a higher mass main sequence star than this one, so that it evolved off its main sequence first. So it must have been between sort of 2 and 10 solar masses, went through a planetary nebula stage, and ejected its outer layers, and just left a 1 solar mass white dwarf star now in this system. Okay. So we're now going to move on to the spectroscopic binaries to look at those to see how we can derive masses from these. So just a heads up, so the next couple of parts here is probably the most mathematically complicated we get in the module. Don't worry about it too much, but the equations get a little bit involved. But they do lead to some fantastic discoveries, as we should see. so bear with it. Okay, so in this case, we're going to, as I say, you only see one star in the sky, so the only way to find out that there are two stars there is to look at their spectra and to use the fact that if there's any motion of the star over time, then that can be revealed by a change in its radial velocity due to the Doppler shift. So just to recap, the Doppler shift is the fact that spectral lines will move towards the blue if a star is coming towards us, and lines will move towards the red if the star is moving away from us. I'm sure you've met Doppler shift before. You may have seen quite complicated looking formulae for it in all sorts of different circumstances. But in astronomy, we just use this form, which looks a lot simpler, so I would recommend you stick to this form. So we're talking about a change in wavelength relative to lambda naught, which is the rest wavelength. Sorry, I should have said that there. So lambda naught is your laboratory wavelength, rest wavelength, if you like. And delta lambda is the shift in wavelength from that. So it's the observed wavelength minus the rest wavelength. And that ratio is the same as the radial velocity of the object relative to the sun divided by c. So VR here is our relative radial velocity. Okay, so that takes out a lot of the complication that you might have met in previous Doppler formulae, where you're trying to work out whether the observer is moving or the emitter is moving. Here, we don't really care. It's just relative motion. Okay. So we now need to alter Kepler's third law to take account of the fact that we're not going to be able to see A at all. We don't see two stars, so we obviously can't measure the angular separation or the physical separation of two stars. The only information we're going to have is from the velocities. So let's go back and look at how we can bring velocities into this. So these are the circular velocities. We introduced these before. So if you've got star 1 with an orbital radius of r1 going around with a period p, its speed will be given by 2 pi r1 over p, and the same for v2. Now we have to bring in the complication that our system is going to have an orbital plane inclined at some angle I, and so therefore we only see a certain component of the true circular velocity. We don't see necessarily the full component of radial velocity. And if you think about it for a moment, then that is to do with, that'll be modified by a factor of sine I, where I is the inclination angle. So you remember if the inclination angle I was 90 degrees, then the orbital plane is like this, and the stars, if we could see them moving, would be going like this, but they're basically going like this. So the orbital plane is perpendicular to the sky. So I is 90. So in that case, the star will be coming straight towards us or straight away from us at these points in the orbit. And so therefore we are seeing the full radial velocity in that case. So sine I will be 1. If the inclination angle was 0, the orbital plane would be in the plane of the sky, and the stars would just be going around like this. And so in that case, you never get a component towards us or away from us because the motion is all in the plane of the sky. And then, of course, sine I is 0 and the radial velocity is 0. So if your orbit was face on, then basically you wouldn't know there was a binary system there at all. Okay, and normally in these cases we don't actually know what I is. That's the problem. So this time we don't have a way of working out I usually, unless it's a special case. Okay, so for these spectroscopic binaries, we can split them into two different classes as well. And so the one we're going to look at first is what we would call a double-lined spectroscopic binary. And that means that both sets of spectral lines from each star are seen. Okay. So this is illustrated here. with two of these kind of, again, photographic type spectra of a spectroscopic binary system, a double-line system. So in the top spectrum, you can see that each line is doubled up, if you like. There's one here and one there. And you've got a whole set of lines, and they're all spaced apart by the same amount of wavelength shift. Okay. And this second spectrum here is taken at a later time in the orbit, and you can see that the lines have all merged into one. Okay, so now you can only see one set of lines. Okay. So here, both stars look fairly similar. In fact, they must almost be exactly the same spectral type because you've got the same set of spectral lines. They don't have to be, of course. But of course, you don't want one star so faint that you can't see its spectral lines in the combined spectrum of both stars. So you need them to be perhaps a reasonably similar brightness for this to work. Okay, for you to be able to see both lines. It becomes a contrast effect. Okay. Well, let's look at a little movie that illustrates this a little bit more. Okay, so here's a star orbiting around its center of mass. Okay, and down here you can see the resulting effect animated in their spectral lines. So when the star is moving towards the Earth, so at this point in the orbit, those lines are shifted to the blue. So these represent the rest wavelengths here. And when the star is moving away from us on this side of the spectrum, you can see that these lines are shifting to the red. Okay. And they all shift together. Okay. So that's illustrated a bit more on this plot. So here you've got, again, a schematic of a spectroscopic binary system at the top, with some elliptical orbits this time, similar mass stars by the looks of it. And so you can see the changing set of lines as the stars are in different parts. So the Earth is this way. So here star A is coming towards the Earth. So the spectral lines from star A are blue shifted, but the spectral lines from star B will be red shifted. And so you get a maximum splitting between the two lines there. At this stage of their orbit, they're both moving sideways. So the lines merge. Over here, switched over. B is coming towards us, so B is more blue shifted, and so on. And the way this data is normally presented is what we would call a radial velocity curve. So you plot the radial velocity of each star, each set of lines, as a function of time, okay? And then each star will trace out a curve, okay, an oscillating curve. And of course, again, both stars have got the same period. So you go through one cycle, in this case, 16 days on this example, is the period of the orbital motion. So you know the period, so that's good, just from the radial velocity curve. You basically wait for the spectral lines to go through one complete cycle, and you can see both stars. One effect, of course, that you can see here as well is that these curves are not perfect sine waves, and that's because in this case, and probably in most cases generally, the orbit is elliptical rather than circular. So remember, star B here is a long way from the center of mass. It'll be going slower at this bit of the orbit, and it'll be going faster at this part of the orbit. So that changes the slope of these lines. So the star's going faster here and slower over here. Okay, so you can also determine the eccentricity of the orbit of each star from this as well. Okay, because of the deviation from sinusoidal, a pure sine wave. Okay, and you're looking to measure the amplitude of, effectively, if you think of it as a sine wave, what's the amplitude of the sine wave? So what's the motion when it's coming towards us here, okay, or away from us here? So one of these peaks. So this is the peak to peak, but you want half of that, okay? That's what you need. Okay. I'll set you a little problem at the end to think about that. Exactly what you measure off these curves. Okay. But that, when we talk about so when I talk about VR1, VR2 here, we're really talking about the amplitude of these radial velocity curves. So if we've got data like that, if we've got one of those radial velocity curves, then we can easily measure the mass ratio. Okay, it's just going to be the ratio of the two amplitudes of the radial velocities, because this is related to this by sinai, which is obviously the same for both, so that factor cancels out. And then if you go back to the definition of V1, just 2 pi R1 over P, so P is the same for both, so this is also true. And then this is your center of mass formula again. So you can easily find the mass ratio, but this time it's a bit more difficult to find the sum of the masses. So as I mentioned, we can't see A anymore, or R1 and R2. We haven't got any spatial information. We've only got velocity information. Okay, so let's see how far we can get. Well, we need to replace the stuff we can't see with the stuff we can see. So let's bring in the definition of circular speed again here. So that gives us this formula here. And again, we measure the radial velocity, not the full component of circular speed. So we need to bring the sinai factor in here. But that's as far as we can go. Often we don't know what sinai is, but at least we've got the radial velocities in here. So we can use this expression to substitute our A in Kepler's third law and substitute this in instead. So this starts to look a bit complicated, but you can see what's happening here. So this is our original Kepler's law. We want to get rid of A and replace it with this. So we're just going to cube all of that, okay, and that simplifies down here. Okay, so you've got P over 2 pi cubed here, so that cancels out P squared on the bottom to leave P there, and you've got 2 pi cubed on the bottom, which leaves you one factor of 2 pi there. Okay, so like I say, often we won't know what sinai is. Obviously, it's a number between 0 and 1, but for an individual system, that's not much help. If you've got a whole lot of these systems, then sort of an average value here would allow you to make an estimate. But of course, it is cubed, so it's often fairly uncertain. So you can't always necessarily work out the individual masses. You only get a lower limit to the sum of the masses. Okay, so if you put sinai of 1 in here and work out the sum of the masses and use the ratio before, then that will tell you a lower limit to each mass. But you do know the ratio. Okay, so put that one into, to have a break now and put that one into action. So just use the formula we've just taken with this data. So imagine you've got a double-line system. You've got amplitudes of 150 and 350 kilometers per second. Just keep an eye on the units here. And it has a period of 8 hours. Okay, so this is much faster. So remember, spectroscopic binaries, which are unresolved in the sky, are typically going to be much closer together. The two stars are physically closer together. And because of Kepler's law, that means we're talking about shorter periods as well. So, 8 hours is nice. You can follow this object going all the way around its orbit in one night. Okay. Using a series of spectra. So to make it tractable, just assume that this system is close to edge on, meaning that the inclination is basically 90 degrees. Okay, so that's sinai is 1. Okay, so calculate the individual masses, again in solar masses, using that data, so you can see how that formula works. So have a go at that one, and I'll see you after that.